Today, on How It's Made. Photographs. A developing story. Fur tanning. Hair care secrets revealed. Welding electrodes. A meeting of the metals. And electric violins. We'll plug into the process of making them. In the 1830s, the first photographers used light-sensitive chemicals to capture images on paper. Today, machines do much the same, but with amazing speed, accuracy, and versatility. It's a tried-and-true method many people still prefer to make their memories into pictures. The photo lab receives envelopes containing rolls of film for developing. Processing will turn each exposure into a negative image and then a positive. That positive is what we know as a photograph. A scanner takes a digital photo of the order details specified on the packages. It tracks things such as the print size and finish, and the number of copies you ordered. A conveyor then sorts the envelopes into bins, grouping them with similar orders. Next, a machine extracts the film rolls from the metal capsules in total darkness. Exposing the film to light would ruin the photos. The envelopes go into bundles so they can later be rematched with the right pictures and negatives. Here's what the machine looks like inside. A blade cuts open the metal capsule and another slices off the leader. The machine unravels and lines up as many as 60 meter-long films end to end. A sticker joins the ends and identifies each film with a barcode. The machine measures the assembled strip, then winds it onto a reel inside a metal box. Another machine unwinds the reel and runs it under a non-damaging infrared light so that a technician can check for tears. Just one tiny tear could jam the machine and ruin all the photos. If the tech does find a tear, he repairs it by hand. He puts his arms in the machine's little darkroom so as not to expose the film to regular light. First, he applies tape to reattach the area. Blades then cut the tape evenly on both sides. The worker is able to see what he's doing on a TV monitor hooked up to an infrared camera inside. Developing the exposures requires 4 chemical baths still in the dark. In the first, sulfates make the image appear as a negative. The second includes acetic acid to halt the effect of the sulfates. The last 2 baths preserve the image and rinse away chemical traces. To print the pictures, workers load the negatives into yet another machine. This one contains light-sensitive paper. All it takes is a flash to transfer the image. But that light is powerful, almost as bright as the sun. A sensor instantly adjusts the intensity to correct any improper exposure by the photographer. To develop the prints, the paper goes through 4 chemical baths similar to those used for the negatives. 1 bath reveals the image, another stops that process, and 2 more preserve the image and rinse off the chemicals. What's different this time is that the paper then heads into an oven to dry for 2 minutes at 71 degrees Celsius. Now a technician marks the pictures that are too bright, too dim, or out of focus, and removes them for redevelopment. Next, a machine unwinds the strip, scans the barcodes, and cuts out the pictures that belong together. It also cuts the negatives into numbered strips of 4. A worker now slips the proper photos and negatives into an envelope. The computer shows her what to include, and a machine provides the original package the film came in. When you get your photos, you can check them against your original order. That way, you can ensure that everything's picture perfect. Fur has been in style since prehistoric times. Talk about a fashion original. In those early days, fur garments were pretty basic. Their main purpose was to keep people warm, a primary need. These days, fur is often a fashion choice, but it still provides old-fashioned warmth. At the tanning plant, a worker sorts through raw beaver pelts purchased at auction. He inspects the quality of the hair, then determines the type of garment they're suitable for. He hammers a lot number into the underside of the pelt. It perforates the skin. This technique is used so that the number stays on the pelt during processing. Using a pneumatic punch, he cuts out the ear cartilage. It's a crucial step. They need to get rid of the cartilage early on so the pelts can go through certain machines during tanning. The pelts are a bit dried out because of preservation techniques used before they were delivered to the tanning plant. To rehydrate them, they put them through various chemical washes. The final bath contains tanning chemicals. They convert the underside of the animal's skins to leather. The supple leather texture will allow the pelts to eventually be shaped into garments. Between each wash, the furs go into a wringer. It spins out the excess liquid. Moisture has caused the pelt to thicken, so they thin it down with a spinning blade called a flesher's knife. You need to be an expert to wield this tool. One false move and you'll cut into the follicles and lose fur. Next, a worker shovels sawdust into a big drum. He gathers up the pelts and places them in the drum along with the sawdust and adds a mineral solution. The drum turns, tossing it all for about half an hour. This cleans and conditions the leather side of the pelts. The furs emerge still damp, so they hang them to dry over wooden dowels, leather side up. The rest of the sawdust will fall away in subsequent operations. Now, a worker scrapes off the pelt's long hair to expose the downy undercoat. This undercoat has a more desirable look and texture. He rubs a generous amount of oil into the leather of the pelt to lubricate it. Then he tosses the pelts into a kicker box, so named for the automated kickers. The kicking action causes the oils to penetrate the skin. Next, a spinning metal wheel tugs at the pelt to stretch it. A worker cuts away the ragged edges. And and it's into the hot press. This irons and adds luster to the fur. After a quick brush, the pelts get one more press. Then a shearing machine cuts the hairs to an even length. Finally, they bundle up the pelts for a trip to the garment factory, where they'll be great design material. More than a century ago, welders first fused two metal surfaces by melting a metal stick over them using an electric current. That stick is now called a welding electrode. It's the simplest and most popular way to weld. Farmers and mechanics often use this useful tool to repair heavy machinery. This company's electrodes are coated with powdered metals and minerals. During welding, the metals melt and the minerals protect the area from oxygen, which would weaken the bond. The electrode transmits an electric current that heats and melts both the electrode and the metal surfaces, welding them together. Thin metal wire forms the electrode's core. The kind of wire depends on what the electrode's designed to weld, but most often the core is made of carbon or stainless steel. A machine simultaneously spins and bends it, evenly reshaping the wire till it's completely straight. 4 metal rollers then push and guide the wire into a guillotine. The blade chops the wire into segments that'll become the electrode cores. These segments range from 25 to 45 centimeters long. The factory puts a variety of metals and minerals in the coating. The metals are often nickel, manganese, and iron. The minerals, alumina, magnesia, and limestone. They also add a colorant to differentiate the models. Workers mix the ingredients with a bit of glue until they turn to the consistency of wet sand. A worker then packs the mix into a machine that forms it into slugs with a hole down the middle. He adds a plastic cap. Then a metal cover slides on and the machine takes over. It takes only a minute for the machine's piston to compress the powder into a solid. Now to put the powder coating on the core wires. A worker loads 4 slugs into an extrusion press. It'll apply 120 tons of pressure on the slugs to shoot the powder through nozzles that'll coat the wires as they pass through the slug's hole. To load the wires into the press, they first stack them in this feeder. The opening at the bottom's adjustable for different diameters because core wires range from spaghetti thin to pencil thick. These rollers pass them through the press one at a time. Four wheels then pull the wires from the feeder into the extrusion press for coating at a rate of up to 1,000 electrodes a minute. When the coated electrodes emerge, they hit a metal wheel that positions them on a conveyor. A sander removes up to 5 centimeters of coating from the bottom, where you grip the electrode, and it bevels the tip so it conducts electricity even better. A worker now checks for uneven coating and to see if the wire's well centered. The coating dries at room temperature for up to 72 hours. To cure the coating, workers put the electrodes in an oven heated to 485 degrees Celsius for up to 5 hours. Once they've cooled, the electrodes head into a printing press. An ink wheel first prints the model and type of current that's required. Another ink wheel then applies a color to the gripping end. It's another way to differentiate the model in case the lettering on the side rubs off in storage. From there, it's off to packaging. An optical scanner counts the electrodes, then a stacking machine separates them into 3.5 to 5 kilogram bundles. Finally, a worker inserts them into cardboard canisters. He adds a piece of cardboard to compress them tightly for the trip. A sticker marks the contents and tape keeps the package tightly sealed. And to that we say, weld done. The invention of the electric violin was all about turning up the volume. It was back in the big band era, and the sound of the traditional violin was overpowered by the horns and drums. Amplifying the violin changed everything. Suddenly, it wasn't just background sound. It was part of the show. The wired violin comes in different shapes because it doesn't rely on the body to resonate sound. This craftsman builds his electric violins one piece at a time, starting with the neck. He traces the shape onto a piece of maple. Then he outlines the top plate. He uses walnut for the lower bout or bottom part, as well as for the backbone of the violin. Next, he cuts out the shapes using a bandsaw. His goal here is to be very precise, because the closer he cuts to the outline, the less sanding he'll have to do later. The dimensions for the top and neck are exactly the same as a traditional violin, so there won't be any difference in the reference points the violinist relies on. The lower bout is very stylized, and the head is more streamlined than a traditional violin. There's no decorative scroll. Next, he chisels out a cavity in the head of the violin to create the peg box. He carves parallel grooves onto the back to give it a snazzy look. Using a rasp, he shaves the wood to the correct thickness. He drills holes for the tuning pegs into the side of the peg box, one for each of the 4 strings. He files down the grooves on the back a little more. Then he scrapes the rest of the neck to give it a final finish. Using a reamer, he tapers the peg holes. The ebony pegs have matching tapers so they fit snugly into the holes. He checks to make sure everything measures up. Now he brushes wood glue onto the neck section and presses the ebony fingerboard onto it. He wraps them with surgical tubing to hold them together while the glue dries. He drills 2 assembly holes in the top piece and makes corresponding holes in the other parts. He smooths the edges of the backbone with an oscillating sander. Then, using a high-speed router, he bevels the lower bout piece to give it a clean edge. He rubs teal-colored stain into the wood because loud colors seem appropriate for these high-volume instruments. A crystal has been glued into the violin's wooden bridge to generate electricity from the string's vibrations and create sound. He pulls the wire from the bridge through the backbone and then mounts the bout to the backbone. He bolts an ebony chin rest on top. Next, he attaches the neck to the rest of the assembly. He loops on the ebony tailpiece. He pulls a string from the tailpiece to a peg. The act of tightening the first string raises the bridge, which will be held in place only by tension. Now it's time to hook up the violin to the amplifier and let the music tell the rest of the story.